to the final presentation of Advanced Building Performance Modeling, in which I will use simulations to assess natural ventilation. Focus will be on the effect of window design, taking the case of a school building in New Zealand. Almost all historic buildings were ventilated naturally. They were compromised by the addition of partition walls and mechanical systems, but with an increased awareness on cost and environmental impact of energy use, natural ventilation became an attractive method for reducing energy and cost. It also provided acceptable indoor environmental quality and maintained a healthy, comfortable, and productive indoor climate. Natural ventilation can be used as an alternative to air conditioning plants, saving 10 to 30% of total energy consumption. This video will comprise of a climatic analysis of the proposed building, an exploration of the site and building description, and finally an overview of New Zealand Building Code. Auckland is located in North Island of New Zealand and is characterized by high urban population. Its climate is classified as subtropical with warm, humid summers and mild, damp winters. Auckland is the warmest and sunniest main centre of New Zealand with an average of 2,003 sunshine hours per annum. The average maximum daily temperature is 23.7 Celsius in February and 14.7 Celsius in July. The absolute maximum recorded temperature is 34.4 Celsius, while the absolute minimum is minus 3.9 Celsius. As shown in the schedule, January, February, and March are the hottest months of the year. Humidity is commonly between 70 and 80%. The prevailing wind direction is southwest. On average, the wind speed range is between 4 to 7 meters per second. In September, the wind speed can reach 11 meters per second. January and February are considered the windiest months. Site chosen is in Ponsonby district in Auckland, New Zealand. It is located in a residential area with no school around. The plot size is 44 by 60 meters squared. It is surrounded by trees from the northwest and the southeast, and it is in close proximity to two buildings. These all have been taken into consideration during the modeling phase to make sure of the accuracy of the results. The selected building is a two-story primary school. Each floor of the building has 5 classrooms. The building is designed based on the minimum building standard of New Zealand. The window-to-wall ratio is 30% as recommended. The Building Act 2004 enforces the building code in New Zealand. The area of the building code which relates to thermal performance in new construction is called H1. Natural ventilation is specified in 3 standards: New Zealand Building Code Section G4, designing quality learning spaces, indoor air quality and thermal comfort, and designing quality learning spaces, ventilation and indoor air quality developed. According to the standard, the minimum requirements vary according to the climate zone. Auckland is located at Zone 1. The standard also addresses natural ventilation in schools as an important factor in helping children learn. The standard also provides a key performance criterion related to IAQ and ventilation in educational institutions that includes the carbon dioxide level. Moving on to IES simulation. Weather data was first assigned on IES, followed by downloading the construction library of New Zealand Building Code and creating a construction template. Occupancy daily profiles were assigned according to the New Zealand Building Standards guidelines. Thermal templates, internal gains, and infiltration rates were set. As for the optimal orientation, suncast simulation was conducted. The Apache simulation revealed that the west orientation is the optimal orientation that achieved the lowest energy. The focus of the study is on the effect of window design on natural ventilation. For this purpose, three main parameters have been studied. First, the openable area, second, the window type, and finally, the window-to-wall ratio. This schedule summarizes the scenarios. The first three scenarios investigate the different openable area percentages of 20, 50, and 75%. The second three scenarios investigate different types of windows, louver, top hung, and casement. And the last three scenarios investigate 10 to 50 to 15% window-to-wall ratio. First scenario, second scenario, and third scenario. The results of investigating the openable area was compared with the case of fixed window. In terms of total numbers of hours where air temperature is within the thermal comfort range, the number of hours is increased 3 times comparing fixed window with other scenarios. Comparing between the three scenarios, 75% openable area achieved the highest number of hours within comfort range. 7th of February was selected for the simulation as it is the hottest day. Comparing the scenarios with the fixed window, the temperature of air is improved by almost 8 degrees and most important, carbon dioxide level is enhanced. Comparing scenario 1, 2, and 3, we can see that scenario 3 achieves the best result in terms of air temperature, carbon dioxide concentration. However, the relative humidity in scenario 3 is higher than the others. In terms of solar gain, there is no change between the scenarios. The psychometric chart shows that better thermal comfort is achieved by natural ventilation. However, comparing the three scenarios, there was no big difference in thermal comfort level. The airflow on the 7th of February for all scenarios is shown. Looking at CFD simulation, for each parameter, the maximum and minimum value on the scale is compared between the scenarios. First, the air velocity. Scenario 2 with 50% openable area showed the lowest air velocity. For air temperature, the best range was found in scenario 3. Air pressure indicates the air circulation within the building. The bigger the range, the more chance of air movement. According to this scenario, 1 has the biggest range. The results of the predicted mean vote show that scenarios 2 and 3 perform better than scenario 1. According to the results, the openable area is 75% in case of sliding window and 30% window-to-wall ratio. Moving on to the effect of window type. First louver, then top-hung, and casement window type. These will be compared with the winner of the first round of simulations, sliding window, 75% openable area. Fourth scenario, fifth scenario, and sixth scenario. Number of hours within comfort level, scenario 6 of casement window type achieved the same number of the hours as scenario 3. In terms of temperature and CO2 level, none of the scenarios achieved better results from scenario 3. Relative humidity is the lowest in scenario 4. No notable difference is in the psychometric chart, all scenarios achieving comfort. This is the airflow of scenario 4, 5, and 6. For CFD simulation, air velocity is the best in scenario 5. Scenario 5 achieved best in air temperature. Scenario 5 has the largest pressure range. PMV in scenario 5 and 6 are almost the same but better than scenario 4. Best in this group is scenario 6, casement window, 30% window-to-wall ratio and 75% open. Best in all scenarios is scenario 3, sliding window, 30% window-to-wall ratio and 75% open. Moving on to the effect of window-to-wall ratio. First, window-to-wall ratio at 10%, and then at 50%, and finally at 15% window type. These will be compared with the winner of the first and second round of simulations, sliding window, 75% openable area. Number of hours within comfort level, scenario 9 of 15% window-to-wall ratio achieved the highest number in the group and also exceeded the scenario 3 results. In terms of air temperature, carbon dioxide level, none of the scenarios achieved better results from scenario 3. Relative humidity is the lowest in scenario 4. Scenario 8 achieved the lowest air temperature and carbon dioxide concentration levels, while Scenario 7 achieved the least humidity. There was no noticeable difference in the psychometric chart. All scenarios achieved comfort. For CFD simulation, air velocity is the best in Scenario 8. Scenario 7 achieved best in air temperature. Scenario 8 has the largest pressure range. And Scenario 9 performed better in the PMV. Best in this group is Scenario 9, sliding 15% window-to-wall ratio and 75% open. Best in all, Scenario 3, sliding window, 30% window-to-wall ratio and 75% open is still the best. Moving on to the final part of this presentation, the building automation system.